Okay, exercise 10e, consequences of the factor theorem. The factor theorem has a number of straightforward but very useful consequences, all right? It's just a property of the polynomial, equations or functions. So I'm just going to go through that with you, okay? It's all coming from the textbook, but I actually picked something that's important, I think that you need to know. Well, the first thing is the first two things is the distinct zeros and all distinct zeros. So suppose that like we have alpha 1, alpha 2, alpha 3, alpha 4, and it goes on. So we've got like those numbers are distinct zeros. Distinct means they're all different. Zero means they are the solutions of the polynomial equation of px. Then x minus alpha 1, x minus alpha 2, x minus alpha 3, and it goes on. They're just a factor of px. It does make sense. If you think about the other way around, if we have the polynomial function that is factorized in terms of, for example, x minus 3, x minus 4, x plus 4, x minus 5, and x minus 2 is equal to 0. So for example, if that's the polynomial equation already factorized in terms of factors, then the zeros of this polynomial equation will be just x equal to 3, x equal to 4, x equals to 5, x equals to 2. So therefore, if we're given that, those each of the the solution here are distinct zeros of the polynomials, then we can go reverse engineering, and that just means we've got those as the factor of the polynomial expression or the polynomial equations. So this makes sense with the first property, okay, or the first consequences. That's pretty easy to understand. All right, so the next one is very similar to the first. Suppose that alpha 1, alpha 2, alpha 3, all the way to alpha n are the n's distinct zeros of the polynomial px of degree n. All right, then the px can be written as this function here. Okay, as you can see here, they include an a in the front, and that a is just the leading coefficient of px. It does make sense as well. For example, if I have equations where x equals to 1, x equals to 2, x equals to 3 are the zeros, then the polynomial function can be written as x minus 1, x minus 2, x minus 3. But then we can also write down the polynomial function as like 2 bracket x minus 1, x minus 2, x minus 3. The coefficient in the front here does not change the value of zeros, okay? Because if you're letting this one is equal to 0, all you have to do is you let each of the terms or factors equal to 0. So it doesn't really matter what is the number in the front or what is the leading coefficient. So you can have any leading coefficient where the root is still equals to 1, 2, and 3. So therefore, if they give you questions where those are the roots of the polynomial equations, then you can have like unlimited number of supply of polynomial function that or equations that gives you those roots here, because you can always change this number to any numbers that any numbers. Can be integers, can be rational numbers. It doesn't really matter at all. Okay. All right. So for these two properties, let's just look at one examples from the textbook. So I'll probably just using the example from the textbook to go through each of the properties and consequences of the factor theorem. An example we're looking at here, I'll just say this is an example 1. It's a very simple example from the textbook. So it's just, we'll just do question 1c. The question asks you to use the factor theorem to write on in the factor form a cubic polynomial with leading coefficient. So it actually tells you what the leading coefficient, 6, and zeros at 1/3, -1.5, and 1. Okay, so this is the question. All right, the question asks you to find a polynomial, or to use the factor theorem to write down in the factor form that is first it's a cubic polynomial, and then the leading coefficient is equal to 6, and we've got 3 zeros here. All right, so according to this property here, then we should be able to write down the polynomial without any problems. It's actually pretty easy. So the px is equal to, firstly we write down the leading coefficient that's equal to 6, and then we can write down in the factor form with all the zeros inputted into here. That's what we are going to get. Okay, that's what we have. And then what you can do is, if you find this is a bit annoying because inside the factors you've got 1/3, you've got half. What you can also do here is break the 6 into 2 and 3. okay? And then what you can do is move the 3 inside this factor here and move the 2 inside the factor there. So in that case, you end up with like 3x minus 1 and 2x plus 1 and x minus 1, okay? That just looks better. I don't think there's nothing wrong when you write down the answer in terms of here. It's okay that you have the numbers inside as a fraction, but I just feel like this looks better, okay? And obviously this question looks like it's designed where you can actually separate the 6 into 3 and 2, where you can put 3 inside this bracket and 2 inside the second brackets there. So it's a very simple question, all right? That sort of like, falling into these two properties here. Okay, all right, so next we're going to move on to the factoring polynomials. We've done this before yesterday. I'm just going to, sort of like, re-emphasize it again. In order for us to factorize in the polynomials, we need to try and error to find as many integer zeros of px as possible. I kind of do agree with this as many integers as possible, but in the real sort of practical problems, I don't recommend students to find every single possible, integer zeros, because sometimes it does take a long time. I do prefer students find a couple of zeros and then use long division to find the rest of the other, factors. I feel like this is an easier way to do it. There is no right or wrong answers here. There is no, strict step-by-step working that you have to follow. That say for example, you have to find at least 2 zeros, or you have to find at least 3 zeros. It's all based on the question. All right, it all depends on the question that you have, and also it's your personal preferences, like what you think it's easier for you to do the question. All right, so I would like to try a question from the exercise. Example 2. Oh. Okay. All right, so example 2, I'm just going to do questions where it says use try and errors. It's going to be question 3. It says using try and errors to find as many integers as possible, and then using long division to factorize the px. So I'll do example 3 exercise, this exercise, and this question 3D, the last one. So px is equal to 9x to the power of 4 minus 51 x to the power 3 plus 85x to the power 2 minus 41x plus 6. Okay, all right, not an easier sort of like a question to do, just because if you look at this question, we also have a leading coefficient that's equal to 9 here. So it's not a very easy question to do here, but that's okay. What we're going to do is we're going to find the leading we're going to use the constant term here at the end, which is equal to 6. And then we're going to just try the numbers to see if that works. Again, you can have a possible, I'm just going to write down all the possible, numbers or factors that you can substitute, and then we can use, long division later on. So I can use plus minus 1, plus minus 2, plus minus 3, and plus minus 6. Okay, and we are just going to do this question by checking the plus minus 1 first. It's 9 minus 51 plus 85 minus 41 plus 6. Okay, let's hope that is 0. Okay, I shouldn't write zeros at all. Let's hope that's equal to 0. So, okay, use my calculator. Oh, okay. Unfortunately, that's equal to 8. All right, so not equal to 0. All right, so try the next one. Minus 1. All right. Oh, where's the minus 1 here? Great, I don't even need to use my calculator. I know this is not equal to 0. All right, unfortunately 1 and 2, 1 and negative 1 is not working. All right, let's try 2. Let's hope 2 is working. All right, so 9 times by 2 to the power 4, minus 51 times by 8, plus 85 times by 4, minus 41 times by 2, plus 6. Looks promising to me. Okay, let's see. All right, yes, it is equal to 0. That's great. Okay, that's really good here. All right, that's equal to 0. Now, then you have a decision. So the decision you need to make here is, are you going to stop finding more zeros, or are you going to continue to do it? Okay, so you've got two sort of like options right now. The first option is you've got a zeros already, which is 2. So that means x minus 2 is one of the factor. Okay, if x minus 2 is one of the factors, then you can use a long division to start the process. Okay, unfortunately, if you do the long division, if you think about it, what's inside a dividend has a degree of 4. Okay, the divisor has a degree of 1, as you can see here. The dividend has a degree of 4, divisor has a degree of 1, so if you start to do the division here, the quotient will have a degree of 3. Okay, so with a degree of 3, if you want to factorize, you have to go through that process again, like this trial and error process again. So it's not ideal to stop at this point. Usually for the power of 4, I want to find at least 2 zeros. Because once I got 2 zeros, I can times them together. So then the degree of the divisor is going to be a 2. So in that case, when I use a long division, the quotient will be a degree of 2 polynomials, which is quadratic, and it's easier to factorize the quadratic. So that's the idea. All right, so yeah, it's up to you. If you feel like you want to do the long division straight away and using the trial and error method to factorize the degree of 3 polynomials, it's totally fine. Okay, you just need to make sure that that you're happy with the method you're using. That's fine. Okay, all right, so I'm just going to do the -2 inside. Now if you think about the previous example with -1, those negative are going to turn this to be positive and that to be positive, so therefore we don't even need to worry about -2. It's never equal to 0. Okay, so it's going to be a positive. It should be a positive all the time. All right, so let's try a 3 here. Now with the 3, let's see. Okay, let's hope the 3 works. Okay, alright, so if you're asking me about an exam, so I need to do all of those working out and keep trying until we get the factors. The answer to that is yes, you have to do it. Hopefully you're lucky enough then when they design the question after the first few trials, you do get the answers. Okay, alright, 3 is also 0, so therefore x plus 3 is another factor. All right, that's pretty good. Okay, so we've got this. All right, so I'm just going to copy this one to the next page, and then I'm just going to continue from the next page. Okay, all right, so continue with this question here. Now we know we've got 2 factors, all right, x minus 2 and x plus 3 here. So what we can do now is, once we have these 2 factors, we can times these 2 factors together. So that gives us x squared plus x minus 6. Now we've got this as a combined factors. After we knowing this, we can start to do the long division. All right. Now you can continue to actually find more factors or more like zeros if you want to, but it's all it's up to you. I would like to do long division now. Okay. Alright, so let's hope this time I'm not going to make any stupid mistake with the long division. So 9x squared, so that becomes 9x to the power 4 plus 9x to the power 3 minus 54x to the power 2. Alright, 51 minus 9 is minus 60, x to the power 3. And I need to minus this one, so that becomes positive 139 x squared minus 41x plus 6. Large numbers, okay? Very, very large, okay? Alright, so minus, let's see if that works. I'm actually a bit scared of this is not the right answer there. Minus 60x to the power 3 minus 60x squared plus 360x. Alright, okay. So now if we subtract, that becomes 199x squared. That looks a bit weird. Alright, what's the answer there? I don't know, it doesn't look very nice. I'm just going to go back and check to make sure everything looks fine. Yeah, okay, see? I know that doesn't look right, okay? I made another mistake, okay? That's P3 here. So if it's this P3, that means that must be a minus instead of positive. And that's the mistake I made, okay? Well, but at least I can actually find out my mistake quite quickly. That's good. So in that case here, I'm just going to change the previous one as well. That's a x minus 3. Okay. All right. Yeah. Most of the time, I'm just making those mistakes to see if you guys are actually pay attention to the online lesson or not. All right. So yeah. All right. Okay, so that gives you x minus 2 and x minus 3 as the combined factors. And then if we combine them together, it becomes x squared minus 5x plus 6. Okay, so I'm going to change that divisor here to x squared minus 5x plus 6. So that just means all of this stuff here, it should be not, or it shouldn't be correct anymore. So I'm just going to remove all of them. Let's continue. All right, 9x to the power 3. Let's start again. That's 9x to the power 4. 45x to the power nope, that's 2. Yep, okay, keep going. 3 plus 54x to the power of 2. All right, I'm pretty scared now. All right, let's hope I'm not. Okay, I'm using my calculator just to make sure I do everything correctly. That becomes minus 6x to the power 3 and plus 85 minus 54. I know the answer, but just confirming the answer here using a calculator. So that's minus 6x to the power 3 plus 30x squared minus 36x. Looks okay. That's x squared. Minus 41 plus 36 is minus 5x plus 6. Okay, perfect, finally. All right, that's plus 1. So therefore, we've got x squared minus 5x plus 6. And at the end, the remainder is equal to 0. All right, so now we have two factors here. All right, now for the divisor, we already know these factors can be simplified into can be factorized into x minus 2 and x minus 3. For the quotient here, that looks like in the perfect square formula. So it should be 3x minus 1 bracket square. Okay, all right, so therefore, after you factorize further, like, you first write down px is equal to x squared minus 5x plus 6, and then 9x, what am I doing? 9x to the power of 2 minus 6x plus 1. Then you can further factorize each of the factors. All right, so you end up with 3x minus 1 to the power of 2. All right, okay, so that's all for this question here. Now, I just want everyone to pay attention to this question. It's a very interesting thing. I didn't mention that previously. If you just pay attention to the last factor here, okay, firstly, that's a double root. All right, so double zeros. So we'll have like two same results when x is equal to 1/3, 1/3. All right, now the question here is, if you just look at the last digit here, which is equal to 6, and then I do ask everyone to, if that's the 6, we need to check it plus minus 1, plus minus 2, plus minus 3, plus minus 6. If you continue this checking process here, all right, say for example, if you do P6, P minus 6, you're checking, obviously that's not the result. You're not going to find a P, 1/3. So where the 1/3 comes from, and why does it go to 1/3? The reason because of that 9 here in the front. Okay, this working out, all right, by checking the plus minus 1, plus minus 2, plus minus 3, plus minus 4, 6, because due to the very last constant number, is when the leading coefficient is equal to 1. However, this time the leading coefficient is not equals to 1. It's actually equals to 9. So potentially, what you can also do is you need to break the 9 into plus minus 1, plus minus 3, plus minus 9. And then you're going to use the factors that are created by the constant divided by the factor that is created by the leading coefficient to find more zeros. So potentially you can have more checking that you need to do. So for example, if I pick 2 here, plus minus 2, with a 3 plus minus 3 there, potentially you can have plus minus 2/3. And then we can also have like plus minus 1/3, plus minus 6/9, plus minus all the other answers. And then that's the problem when the leading coefficient is not equal to 1. You end up with so many possibilities that you need to check, and so that makes this checking process not ideal to use in exams, all right? Because you just don't have time to check all of those, especially if the leading coefficient is not equals to 1. Okay, so hopefully that explains something. So if that's the case, we always still looking for the last constant number, and then we still check, and hopefully we have maybe 1 or 2 roots, hopefully as an integer root. Okay, If we do have an integer root, that's good. All right. In that case, if we have two roots, that's great, excellent. We can perform long division and try to get the result. If we only have one root, one integer root, and you're running out of all the options later on, in that case, I would still suggest you to use a long division, find out what is this number, this expression is going to be, and then you start to perform the calculation where you're going to combine the two numbers here, and to find more roots and do the checking. Okay, so hopefully that makes sense. But usually the question is designed where you can find several integer roots before you need to go more detail into those non-integer roots where the roots is just like it's a fractional root. All right, so that's an example 2. Okay, let's move on. So the next point is the maximum number of zeros. I mentioned that before, okay, which is very simple and easy, but it's important as well. A polynomial of degree of n has at most, I use the word at most, n zeros. So that makes sense, right? Think about these polynomials, right? Think about the linear polynomials where the degree of x is equal to 1. So like just say, for example, if we have x plus 1 is equal to 0, we'll have one root, all right? The n is equal to 1 here, and then we've got one root. Now we'll move on to quadratics, okay? We can have a quadratic equation x squared plus 3x plus 2 is equal to 0, all right? That's just an example. Now the degree is equal to 2, and we have two roots. But remember, for the quadratics, we're always looking for the delta, the discriminant. The discriminant, if it's equal to 0, then we can have one root, or we can say that's a one double root, which is like a two root, but like one distinct root. When delta is less than 0, then we have no roots, or no real roots. We still can have like a complex root, but no real root. So this property still makes sense because they use the word at most. Okay, so therefore, if we have a polynomial with degree of 3, I'm just writing a random polynomials, a degree of 3. When n is equal to 3 here, we can have a maximum of 3 roots. Okay, you still can have like one root, okay, which means it's a triple root. You can have like one real root and two complex roots. That's possible as well, but that's only after you're learning complex numbers in extension 2, so we don't talk about this one in detail. All right, so that's what happens. All right, so just remember, if the polynomial is a degree n, it has a maximum of n zeros or n roots, and that just means you can have a maximum of n factors. All right, so the next one. Identically equal polynomials have the same coefficients. If you check the textbook, I actually skip some of the property which I find is not important. Okay, so I only including the important properties of the polynomials. If two polynomials px and qx are identically equal, they're just equal to each other. That is, px is equal to qx for all value of x. Then the corresponding coefficient of the polynomials are equal to each other. So what does that really mean, okay? If we have two polynomials so that they are exactly equal to each other, okay? If they are exactly equal to each other, then everything is equal to each other, all right? So I'd like to show you an example here to demonstrate this question. Example 3. That's also from the textbook, all right? So there's question 5. I'll just do question 5, B. Okay, if 2x to the power 3 minus 8x squared plus 3x minus 4 is equal to or identically equal to a minus x minus 1 to the power 3 plus b x minus 1 to the power 2 plus c x minus 1 and plus d. Alright, if that's the case, if they're all equal to each other, that means the coefficient must be equal to the coefficient. All right. However, on the right hand side, if you look at it, it's not factorized, or it's not in expanded form. Okay, so you've got two options to do. All right, the first option is you expand all the terms here by expanding this, that quadratic, and expanding all of those, and then equating the coefficient, and then you solve a simultaneous equation. I am not going to do it this way. All right, I'm going to use the method where you just substitute the values. So what I'm going to do is I'm going to substitute the value of x. I'm going to choose the value of x to be a certain value, some special numbers. All right, and then I'm going to create a simultaneous equation with a, b, and c, and d. Okay, so the first one I think I'm going to substitute, all right, is when x is equal to 1. If I substitute x equal to 1 here, all of those disappeared, as you can see. So I only have the d left, which I can substitute 1 inside here as well to get the result for d. So I can get d straight away after I substitute 1 inside. Okay, seems these two are not identically equal to each other, so that means it doesn't matter what number I substitute into the first and second, they must be equal to each other. Alright, so you can substitute any value you like. Alright, so in that case, if I substitute 1 into the left-hand side, I've got 2 minus 8 plus 3 minus 4 is equal to 0 plus 0 plus 0 plus d. Okay, so from here, d is equal to, just use my calculator, I'm lazy now, that's equal to minus 7. Alright, so I've got d equal to minus 7. Alright, the next one is I need to pick the nice substitute as possible. Alright, so I'm going to substitute. Unfortunately, it doesn't matter which one I substitute. I'm not able to cancel any other terms out because they're all equals to x minus 1. So in this case here, I'm just going to find a number that's a bit easier, like 0. Okay, if I substitute 0 inside, I will end up with minus 4 on the left hand side. Okay. And then on the right hand side, I'm going to have minus a plus b minus c plus d. But we know what's d equals to, which is minus 7. Alright, so therefore, if we rearrange these, we've got a minus b plus c is equal to minus 3 here. So that's the second equation I have, alright? So now, as you can see, I've got an equation with 3 letters here, alright, unknowns. I need to have at least 3 equations with a, b, c in it to solve this for a, b, and c. Alright, so I have to keep going. The next one is you're going to substitute let x equals 2. Maybe 2, okay? So if I substitute x equal to 2 inside, okay, that becomes 2 times by 8 minus 8 times by 4 plus 6 minus 4 is equal to a plus b plus c minus 7. All right, so let's do the calculation on the left. All right, so that's minus 14, a plus b plus c minus 7. So a plus b plus c is equal to minus 7. All right, good. So we've got 1, 2, 3. All right, I do need another equation in terms of a, b, and c, but you can substitute any other values again to get another equation in terms of a, b, c. However, I'm just thinking about, is there any sort of easier way we can combine the method for, 1, which is equating the coefficient, with the method 2, which is substitution. Now, this is very, very important. I do want everyone to look at very carefully. Look at the leading coefficient here. I'm just going to highlight it using a different color. This is the leading coefficient, which is 2. Look at the leading coefficient from the right-hand side. The only way you can have a leading coefficient is not from these terms. It's actually from the term here, because that's the highest power of 3. If you expand that, okay, I can expand this, but I don't need to, okay? If you expand it, the leading coefficient is just going to be the a in the front, okay? So that tells you a is also equals to 2. All right, so we can say by equating the leading coefficients we know that a is equal to 2. All right, and that's a very, very important result, because once we know a is equal to 2, we can substitute a equals to 2 into this equation and into the equations here. So therefore, we have like an easy equation to solve, like this now. All right, so now all we have to do is solve these 2 equations. We can call this equation 1, equation 2. Equation 1 plus equation 2, 2c is minus 14, so c is equal to minus 7, and then in that case b is equal to minus 2, and that's all. So we've got our answers. D equals to minus 7, b equals to minus 2, c equals to minus 7, and a is equal to 2. So these are the answers we have. That's all. 1, 2, 3, 4. All right. Okay, so this is the questions where you're kind of using both methods. All right, you're not just restrict yourself into just one method here. Or you're using both methods, where you start to do some substitution to find some value of a or b or c or d, and then you substitute more more values inside. You get equations, and then you decide to find maybe can we find maybe one value of a or b or c first. By equating the leading coefficient, it's much easier. Now, you probably ask, like, why not equating other, coefficient, or the coefficient in front of x to the power of 2? If I want to equate the, coefficient in front of x to the power of 2, think about it. You're going to have coefficient here in front of x to the power of 2. You're going to have another coefficient here for x to the power of 2. So it's not ideal. You've got multiple x to the power of 2 from the expansion of the right-hand side. You want to have just one expansion, right, and just easier, equating coefficient of x to the power of 3 is much easier because you only can have x to the power of 3 from the first expansion. Okay, I really hope that makes sense to everyone. All right, that's good. Let's move on. All right, so this is the last one, okay, the geometrical implication of the factor theorem. It's actually pretty important that everyone needs to know. So for the first one is the graph of two distinct polynomial functions, distinct in their difference, cannot intersect in more points than the maximum of the 2 degrees. So what does that mean? If we just draw a diagram here, for example, all right, if we have a polynomial degree, let's just do a degree of 2, okay, that's a degree of 2, which is quadratic, and let's do a degree of 1, that's a linear function here, so that's a degree 1, that's a degree of 2. All right, now the intersection point you can see here, the maximum number of intersection point is 2. You can't have 3 intersection points, it's just not possible. All right, why is that? And what's the reason for that? Okay, it's actually pretty simple algebraically. Think about it, right? If I want to find intersection point, I need to form simultaneous equation. A degree of 2 means we have like ax squared plus bx plus c. A degree of 1 means we have like mx plus d, for example. If we're making simultaneous equation, making them equal to each other, then I can move this one over to the left-hand side, and I can start to try to solve this equation. If you solve this equation, you should be able to see that entire expression here, this is still a degree of 2. That's the maximum degree, okay, degree of 2, which tells you the maximum number of solution is 2 from the previous properties. And that's the reason why it says the graph of two distinct polynomial function cannot intersect in more points than the maximum of the 2 degrees. All right, so if that's a degree of 3, that's a degree of 1, then the maximum intersection point is 3 points. Okay, I hope that makes sense, right? You can't have like 5 points. It's just not possible. In order for you to have 5 points of intersection, you need to have at least one of the function to have a degree of 5. That's possible. Otherwise, it's impossible. All right, so the next one is, again, very similar to the previous one. A line cannot intersect the graph of polynomial of degree n in more than n points. Well, a line has a degree of 1. If I have a polynomial function of degree of n, then n degree must be more than 1. Okay, so therefore, unless you have 2 lines where they're both equals to degree of 1, in that case they can only intersect at 1 point, unless they are just identical lines here. But that's not possible because we're talking about distinct polynomials. Okay, all right. Now, just going to try the questions here, and then in this question, there's something that I can't really explain to you right now. You guys need to learn a bit more, like in differentiation, and also hopefully that you're learning in extension 2. Then I can explain to you the reason why. But at this stage, I just wanted to actually accept this. All right. So let's look at example 4. Okay, I'm just picking an example from the exercise, and again, question 12a. It says here, by factoring the difference fx equals to px minus qx. All right, now they ask you to describe the intersection. Describe the intersection. Okay, intersections between the curves px and qx. All right, so the question here is px is equal to 2x to the power 3 minus 4x squared plus 3x plus 1. The qx is equal to x to the power 3 plus x squared minus 8. All right, now the reason why they say by factoring the difference. Now, think about this. If I want to find the intersection point, I need to make sure that px is equal to qx, all right? Then if I need to solve an equation, I need to move the qx, I need to move the qx to the left-hand side. So, like this. And now I need to solve this equation. And that's the reason. All right, so therefore, that's why they're saying by factorizing px minus qx. All right, so let's just start with the process here. First, I'm going to let them equal to each other. Okay, and then if you look at this from the previous results here, the maximum power here are both equal to 3. So therefore, we can have potentially a maximum of 3 intersection points. Potentially maximum of 3 intersection points. Okay, you can have 2, which means one of the point may be a tangent to the graph. Okay, it's like a double root. But again, this is the stuff I have to teach you later. That's x to the power of 2 plus 8 equal to 0. All right, so we end up with this polynomial equation to solve. All right, in order for us to solve this polynomial equation, what we need to do is we need to perform the long division, we need to check and try and error to find it, we need to factorize, okay? So I'm going to start to factorize this. All right, let fx equals to x to the power 3 minus 5x squared plus 3x plus 9. We're going to check f1. I don't think that's equal to 0. Okay, check f negative 1. All right, perfect. That is equal to 0. So we've got, so therefore, x plus 1 is a root. Now you can check more if you want to, but I've just decided to do a long division. Okay, it's totally up to you if you want to check more or not. I just have a habit, like, for the power 3, I'll just find one solution and then I'll perform long division. All right, cool. So I've got the answer. That's really good. All right, so we've got x squared minus 6x plus 9. All right, so I'm just going to put it here. Now I've got this fx equals to x minus 1, or is it plus 1? It's plus 1. And then x squared minus 6x plus 9. All right. And then I can further factorize the second factor, which is x minus 3 squared, which is, a perfect square. All right, so once we've got this result, now you need to describe, okay? You need to describe the intersection. And this is the way I need to ask you to sort of now you just accept this result here. So right now we've got 2 intersection points. So firstly, I'm just going to write 2 intersection points. All right. Remember, we should have a maximum of 3 intersection points, but right now we have 2 intersection points. The first one is when x is equal to minus 1. The second one is when x is equal to 3. All right. Now, to further describe this, the graph, this 2 graph is going to just pass through at x equals to negative 1. So they're going to intersect at x equals to negative 1. Simply just pass through, or at an angle. Right, so what does that mean? It's just like, you have a curve and then you have a second curve. They just intersect, okay, like this. However, for the second one, that x equals to 3 has a double root here. Well, if you look at the power is equal to 2, so it's like a multiplicity of 2. And I will explain to you what I mean by multiplicity. All right, so in that case here, the conclusion for that is they are going to intersect at x equals 3, but they are tangent to each other. Okay, so these 2 curves are tangent to each other at x equal to 3. All right, now how do you know? Okay, so at this stage, I just wanted you to remember this. If you have a power that's more than 1, it's going to be a tangent to each other. All right, so they still intersect, but they're tangent to each other. So it's like, if I draw a diagram, it's like you have a curve here, then you have another curve like this, where they still intersect. However, they don't go across each other. All right, they're tangent to each other. All right, that's the key. That's the key. So I can't, sort of prove to you right now. You need more information about differentiation, which I eventually will let you know. But right now, I just wanted to accept this when it comes to the questions. All right, so that's all for this lesson. It's a pretty long lesson at describing all the properties of the polynomials, and I really hope that everyone enjoyed the lesson. All right, thanks for watching.